We're going to start looking in Unit 1.4 at dynamics. Now, dynamics and kinematics are intimately related. Kinematics is the motion of an object without considering what causes that motion. Dynamics is now the study of motions of objects, but we're concerned about what causes motion. Why does motion change? What causes accelerations in objects? So dynamics is the study of the forces that cause the motion of objects and systems. And we'll talk about what systems are in a little bit. But we're dealing with forces now. Now, forces cause changes in motion, right? You push someone, they change motion. The force of gravity changes the motion of an object as you drop this marker. Now, forces can be thought of as pushes or pulls on objects. Sometimes these pushes are direct, like the example I used, pushing someone, or if someone's on roller skates or a child on a swing, pushing them on the swing changes their motion. But there's a physical contact there. You literally have to go up to the child on a swing and physically push them or pull the swing to get that motion to occur. Sometimes these forces can be spooky action at a distance, if you will. Gravity, for instance, right? The Earth is pulling down on this marker, even though the Earth and this marker are not in physical contact with one another. Protons, positive charges, will repel one another without coming into contact. Negative charges will repel one another without coming into contact. Positive and negative charges will attract one another without coming into contact. They don't have to physically be attached to one another. So forces don't have to occur through physical contact, although a lot of the forces that we'll be dealing with the exception of gravity, are physical forces. A rope tied along a log pulling the log, or towing a car, or a crane lifting an object. Now, forces have both magnitude and direction. Right? So forces can be light forces or heavy forces. I can punch this wall, or I can use a wrecking ball to knock the wall down. So the magnitude of a force can change. I can pull gently on a rope, or I can really hook it up to a truck and pull much more strongly on a rope. And direction. Direction matters depending on the motion. Right? If I tie a rope around a rock, I can lift the rock up, I can pull the rock in any direction, and the direction matters. So forces are vectors. So when we talk about forces, when we add forces together, we can, unless they're one-dimensional, we cannot simply algebraically add forces together. We have to look at the vector addition of forces, which usually means, again, breaking them up into their components and looking at the x, y, and z components, or in the case of this class, mainly the x and y components individually, like we did with projectile motion. When dealing with forces, a good way to understand how forces act on an object is to draw what is called a free body diagram. A free body diagram takes your system or object and draws the external forces acting on that system or that object. So for example, right, we have to identify all the external objects, external forces on an object in order to determine that object's motion. So here I have drawn a very simple example. There is a large box sitting on a floor. So if we want to identify in this simple example all the forces acting on that box, I would have to note, well, the box is being pulled down by gravity, right? There's a force on the box from the Earth. That's gravity. That gives the box weight, and we'll talk about weight later on in this series of lectures. The floor is pushing up on the box, right? The box is sitting on the floor, pushing down on the floor. The floor is pushing back up on the box. There's a force on the box from the floor. And then finally, a person is pushing the box to the right, so there's a force on the box from the person. So if I want to know what the net external force is on an object, and we'll talk about that in just a bit, net external force, the net just means the sum of all the external forces, or the sum of all the forces. External, because it's external to our object, external to the system. The box is our system, right? The box is made up of tiny little atoms. When you push a book or a box, you're pushing on some of the atoms, which pushes the other atoms in the box, and all those atoms move along together. It's a rigid structure. We don't calculate the force on each individual atom. That's ridiculous. But we treat the entire box as a single system, as a single object. And then we look at what objects are outside of this box. What do I mean by an object? Well, what's in the box? Maybe there's a person in the box, hiding in the box. Or maybe there's a television in the box, or maybe there are blankets in the box, or whatever. I don't care. I'm going to treat those objects, whatever's inside that box, as part of the box. That may change the box's weight and how difficult it is to slide the box, but I'm still going to treat that as a system. So free body diagrams are incredibly useful when dealing with dynamics, and you will be drawing these free body diagrams as part of your homework, of course, and I strongly recommend drawing them as part of any assignments you have or exam exercises that you have, because it's, as part of our problem-solving techniques, it helps identify all of the forces acting on an object.